Vertical circular motion. Objective: to study the dynamics of vertical circular motion. One end of a massless inextensible string of length L is fixed to a fixed point O, and its other end is tied to a very small bob of mass m. The bob is given a sudden push at the lowest point, A, in the horizontal direction, so that its velocity is v naught at A. The bob takes a circular path of radius L in the vertical plane. Let's divide the circular path the bob may take into 4 quadrants around point O: 0 to 90 degrees, 90 to 180 degrees, 180 to 270 degrees, and 270 to 360 degrees. Consider the bob at point P, where OP makes an angle theta with the vertical line OA. Speed of the bob at P is v, and it is tangential to the circular path. Let's draw the free body diagram of the bob at P. At P, tension T acts along the radius. Gravitational pull mg acts in a vertically downward direction, which can be split into 2 components, one in the radial direction and the other perpendicular to it. Net force acting along the radial direction is T minus mg cos theta. This force along the radial direction is the net centripetal force Fc, but we know that the centripetal force required to keep the mass m moving with tangential speed v in a circular motion of radius L is equal to mv square by L. Therefore, mv square by L is equal to T minus mg cos theta. Hence, tension in the string is mv square by L plus mg cos theta. If the initial velocity of the bob is very small, it may not be able to achieve angles greater than 90 degrees, in which case it simply traverses back the path it takes. If initial velocity of the bob is greater, it may cross the horizontal line, but will not be able to reach the highest point. When the bob progresses into the second quadrant, tension in the string gradually decreases and becomes 0 at some point. When tension in the string becomes 0, the string becomes slack, and the bob undergoes projectile motion from this point onwards. Minimum initial velocity to complete the vertical circular motion. Consider the case where initial velocity of the bob is sufficient to complete the whole circle. At the highest point B, theta is 180 degrees. Substituting theta equal to 180 degrees in this equation, tension in the string is equal to mv square by L minus mg. If the initial speed is just sufficient to bring the bob to the highest point, tension in the string at this point is 0. Therefore, mv square by L equals to mg, which gives v equals to square root of gl. This is the minimum velocity the bob can have at the highest point. If we take the horizontal plane at the lowest point A as reference, the bob has only kinetic energy at A. At the highest point, the bob has kinetic as well as potential energy. In a circular path, tension in the string always acts perpendicular to the displacement of the bob. Hence, work done by tension of the string is 0 throughout the motion of the bob. As there is no external work done on the bob, mechanical energy is conserved in the gravitational field. Applying the law of conservation of mechanical energy at the lowest and highest points, that is, kinetic energy of bob at the lowest point, half mv naught square, is equal to sum of its potential energy, mg2l, and kinetic energy, half mv square at the highest point. Substituting velocity at the highest point as root over gl, we get half m v naught square equal to 2 mgl plus half mgl. Upon cancelling m on both sides and solving, we get v naught equal to root over 5gl. Hence, minimum velocity of the bob should be given at the lowest point A so that it completes a full circle is root over 5gl. Summary. The minimum velocity a bob should have at the lowest point such that it completes the vertical circle is root over 5gl.